Hey, hello there. Today I'm looking at the question 1439. Find the case smallest sum of a matrix with sorted rows. We have a 2D matrix, m rows and columns. It's called mat. The special property about this matrix is that the rows are sorted. The order is in non-decreasing order. So the first element of every row has to be the smallest, and the elements in the right, towards the right to some prior element, the elements on the right has to be larger than or equal to the elements from the left. So that's the property of this matrix. We also have another integer k as the input. We will see what we need to do with the k very soon. We are allowed to choose exactly one element from each row to form an array. It's rather we are forced to choose one element from each row. So it depends on how we choose those elements. We have different arrays. We want to sum the array up so that to get a total, and we want to find the case smallest total among all the possible arrays we can form. So we have n different choices for every row and m rows. So it's going to be n to the power of m, total number of arrays we can do. Obviously, we wouldn't really want to do that. So that is totally disregarding the property of this matrix. So since that every row is sorted in non-decreasing order, the very first element has to be the smallest. The overall smallest array, the overall array with the smallest sum is basically just be the first column. We can sort of generate arrays in the relatively left-hand side kind of territory to generate enough candidates so that we can just pull the array sum from the pool of candidates k times. We should be able to get the case smallest. We don't need to look all the way back to the very end. So the idea is how we actually gonna go about to generate a certain amount of array so that we are sure when we pull the case smallest, it's gonna be the case smallest overall. So let's look at an example. We have this 1, 10, 10, 1, 4, 5, and 2, 3, 6. So obviously the first column is going to be 1 plus 1 plus 2. The second smallest has to be basically that very first column, but just choosing one of the element from column 2. So the candidates we have for second smallest is going to be 1 plus 1 plus 3, or 1 plus 4 plus 2, or 10 plus 4 plus 3. Obviously, we would go about and choose this one. So it's 1 plus 1 plus 3 equal to 5. And the third smallest, the candidates for the third smallest is going to be the remainder from the prior candidates we generated. And also we explore by sort of like a BFS search kind of fashion from the second smallest. It's 1, 1, 3, so we can consider something like 1, 4, 3. Or potentially 10 plus 1 plus 3. So that's the candidates pool just grow even further every time that we pull the current smallest out. So the third smallest, just by eyeballing it, we see it's going to be this 1 plus 4 plus 3. This is going to be 7. And from that, it's we can sort of expand beyond that. We can have another candidate 1, 4, 3, but it's already there. So we don't want to introduce this kind of duplicates. The other direction we can expand from 1, 4, 2 is going to be 10, 4, 2. And also that we can expand in that direction too. So it's going to be the other candidate that we can have is 152. So let's just copy all of this. And excluding duplicates, the only one that we can introduce now after this one is 152. And I think I'm missing one from the second smallest. The first one we choose is 112. The second one we choose is 113. So beyond those two, we actually have another one. That's going to be 1 plus 1 plus 6. So that's another missing candidate that I'm missing. But yeah, just based on this, you can see it's pretty much like a BFS search from the current candidate, the current smallest k smallest that we have chosen, and just expand beyond that in a level-wise kind of fashion to generate some more array candidate arrays, and put that into the total set of consideration that we have. And because every time we have to pull the smallest, we pretty much just going to be using a priority queue to hold the whole set of candidate arrays. So that's pretty much just going to be how we solve it. The thing on the priority queue is going to be the sum, which is going to be the thing we do this to calculate this priority. But to be able to do sort of like a BFS search to explore the next possible candidates, we're gonna have to store the choices we have made among each row. So it's gonna be a tuple with m plus 1 elements. The first element is going to be the sum for the arrays we configured. The rest of those are going to be the index of the elements we picked in every row. The first one is used for sorting. The rest is going to be used to recording the state of the choice, the actual choice we made, to sum up for that amount. So that's the priority queue and what's on it. And also notice that we kind of see this here. It might potentially be duplicates. Say that we choose 142 to be the second smallest. When we do the neighborhood next level kind of a search based on this, we might be able to introduce duplicate 143 because it's already there. So the priority queue does not do this duplication checks. So for that reason, we will use another hash set to keep track of the candidates we have already generated. So it's going to be a set to do deduplication, and the priority queue to constantly allow us to get the next smallest sum array. And yeah, elements on the array, elements on the priority queue is going to be a tuple of m plus 1 elements. The first is the sum. We use that for priority queue, a priority. The rest is going to be the choice we made to sum up for that. So that's the overall kind of approach. So the elements on there is going to be on the priority queue is going to be upper bound to be number of row multiplied by k. So that's the total number of elements that could potentially be on the priority queue. Every operation is just going to be log time to that total. And yeah, that's the time complexity for each priority queue operation. And we do that for number of row multiplied by k, and then multiplied by log of mk. So that's the time complexity for this approach. So yeah, let's solve this. So let's grab the number of rows and number of columns. We're gonna have a priority queue, which initially just gonna be the global smallest that we can do, the first column with the sum there. So let's do this smallest. And the very first choice, the choice for the smallest array we can do is basically that one. plus 0 everywhere. So yeah, so this is going to be the stuff we put on the priority queue. And we also keep track of the number of elements, keep track of the candidates we generated, candidate array we generated. So it's called, we use a set for this. Just one trick part is array cannot be hashable, so it's not going to be able to put on the set, or we're going to convert that into actual tuples. The reason that I'm using array here is that array is mutable, so we can, because when we try pull the current smallest, we will try to explore in the next level. So we're going to modify the choices, individual choice in there, and also update the sum. So array is mutable. It's just that when we do the checking, duplicate check, we have to convert that into tuple. Yeah, that's pretty much it. I do hope it's hashable, but it's not. I don't think it's hashable. So we're going to do this k times, or k minus 1 times, because we already have the smallest. What we want to do is to yeah, sorry, I haven't put this choice on the priority queue yet. So the previous choice is going to be pulling this from the priority queue. And we decrement the k. Then what we do is to use that as a point to explore all the next possible choices by only modify one of the individual choice we made. So only increment one of this location inside here. So we have number of rows. So we have a number of rows possibilities we can do. So to generate the next candidate array configuration, we first make a copy of this. Otherwise, when we modify it, it's gonna. This is pretty much a reference to that thing. So when we modify that, the value from in there will be changed too. So we don't really want that to happen. So we make a copy. The thing we do is to basically increment one of this location here and update the zeros element. So we subtract the value in the i's location, i's row. So that's mat I, and the original choice for that position is going to be I plus 1, because in here it's padded with the actual total in the zeros position, so it's I plus 1. Oh, sorry, it's colon. Sorry, I'm so sorry. This is the column. Jeez. So if the column is if the current choice in that row is already the last, column, we wouldn't go beyond. So we'll do a really quick check here. I'm sorry. Otherwise, we actually make a copy and try to create a next configuration of a possible array. We do a copy. We subtract the sum with the value from the previous choice, and then we're gonna update that choice and then add the new choice number for that from that row and column combination. Yeah, and the direction we do this exploration is to look at the immediately right for that row. That's the only necessary exploration we need to do every time. So that's that. After we here basically after this 4 lines, we from 112 we basically added this. After this for loop, we basically added 10, 1, 2, 1, 4, 2, and 1, 1, 3 into the consideration set. We generate those, but haven't pushed that onto the consideration yet. We do a deduplication here. That's to avoid from 142 we also generate 143 because it's already generated. So that's this check here. Otherwise, we will do is add this and also push this onto the priority queue. Yeah, so that's pretty much it. Right? So after this while loop, the top element on this priority queue has to be the case smallest. So we return PQ priority queue 0, 0. Is there any problems? Let's run this. Geez, I have to convert this to tuple. Okay, let's push this onto the priority queue. I always make this mistakes. Okay, this time is fine. Let me throw this example on there as well. All right. Yeah, let's see. I think it should be working. Yeah, it's working. Let's look at the time complexity. I think I mentioned that the time here, the while loop, it's gonna run in k times, k minus 1 times, and in each iteration in the while loop, we loop over m of m rows. And so we make a copy, so that's order of m as well. This is constant. This 3 line to update the next array candidate is constant. The convert between tuple and list, I think it should be linear with the size of m as well. The expensive part is this priority queue push. I think it's going to be log of m multiplied by k in the worst case. That's when in the very last iteration of this loop, and it just so happen every time we actually add m minus 1. Not really. Would we really add n minus 1 different choices? No, it's going to be smaller than that, much more smaller than that. We see it here. It's not like we add 3 every time. Almost. Here in this choice, so the first choice we have 1. The second choice, it's among 3. The third choice is among 1, 2, 3, 4, 5. And the third choice actually becomes smaller. And anyway, it's going to be definitely going to be upper bounded by m multiplied by k. But that should be smaller than that because there are duplicates. So we should be able to see that the runtime is k m squared, k m squared plus k m log of mk. So let's put it down here. K multiplied by m multiplied by m plus log of mk. Oh, we also have a pop here, so it's plus k multiplied by log of mk. Yeah, we'll do some rearrange of terms. So it's k. So how much is that? Km squared plus km log mk. This is 1 plus, km squared plus log mk. Or we put that onto the second term. So it's km plus 1 log mk. So that basically gets rid of that. That's be absorbed by m, I think. Yeah, so that's pretty much this. Km squared plus km log mk. That's the time complexity. For space, it's every choice, it's a size of m, and we can potentially have m multiplied by k different choices, so it's m squared k space. Right? That's for the choice, also for the set. Yeah, so depends on how many. Basically, it's m multiplied by the total number of candidates array we generated. This is the heap. The priority queue operation time complexity is also log of the total number of candidates we generated. So I think it depends on the matrix. It can vary, but it's definitely upper bounded by this. Yeah, so that's this question today, priority queue.